So hello everyone, welcome back to our new organic chemistry series. So here today we are starting about the organic photochemistry. So this is the extended version of our radical chemistry course. So here we are talking about the reactions, uh, photochemical reactions, especially in the organic synthesis part. Okay. So basically we have actually divided the photochemistry in the three major segments. The first segment is introduction. In the introduction, we are talking about the light and chemical bonds. Then we are talking about Jablonski diagram. This is the heart of the photochemistry. And the third, we are talking about the photochemistry of alkene. Next, the next segment is the photochemistry of carbonyls. And this particular segment is very much important for your exam point of view because mostly the question has been come from this particular segment. Out of which we are talking about Norris type 1 and Norris type 2. These reactions are very important for any kind of competitive exam. Also, we are talking about Patent-Nobuchi reactions. In our third segment, we are talking about different photo rearrangement reactions such as the dipymethane rearrangement, oxidipymethane rearrangement, azadipymethane rearrangement, and the photophase rearrangement. So with this, we have to now start with our lecture 1 of this particular course, that is Photochemistry Class 1, Introduction and Jablonski Diagram. Now, first, I want to emphasize here that how light actually influence the chemical reaction. First, let us talking about the definition of photochemical reaction. Like a chemical reaction which is induced by electromagnetic radiation, more precisely, we can say that UV or visible light is known as photochemical reaction. That means a molecule is there when the particular molecule is irradiated by using UV light or visible light. So what happened? There is a certain changes has been observed. Basically, the one of the particular electron has jumped from ground state to excited state, and that particular change is actually reason to show different type of reaction. Then we can classify that particular reaction as photochemical reaction since it is a photo-induced reactions. Now, what happened that when a molecule is irradiated with a frequency that is nothing but light. Now, light contains different energy, and when the particular energy, when the molecule absorb that particular energy, and that particular energy is matches the energy difference between the ground state and excited state of that particular molecule, then the transition has been observed, and that's actually leads to do the photochemical reaction. Okay. Now what happened that in a particular organic molecule, there is a different state is there. Now bonding orbital is there, anti-bonding orbital is there, non-bonding orbital is there. So the bonding orbital contains the sigma orbital and pi orbital, and the anti-bonding is obviously sigma star and pi star, and in between there is a non-bonding orbital is there. Now, as the molecule absorb the electromagnetic radiation from that particular mm, light source, that is UV light or visible light, so what happened that energy is actually lead to do the transition, like the electron goes from sigma to sigma star, or it can go for a pi to pi star, or we can get a non-bonding to sigma star, non-bonding to pi star. So this type of transition has been observed, and this type of transition lead to a imbalanced molecular orbital state. Like in a normal molecule, like when it is in the bonding orbital state, the anti-bonding orbital usually empty, but since the particular molecule are actually absorb the light from the external source, that light that is given by external source to the molecule, then some of the electron are actually jump to the anti-bonding orbital, and now the bonding orbital also contains electron, anti-bonding orbital also contains electron, and thus the particular molecule has shows some kind of peculiar reaction. That's why photochemical reaction is not looking like a traditional reactions that is actually observed in a different thermal condition reaction. Also, the photochemical reaction that shows both singlet and triplet state, whereas the thermal reaction is only shows a single state reaction. Now, singlet and triplet state, now you may think little bit confusing, but when you're talking about the Jablonski diagram, just two slides away, then we are talking that you will understand about that singlet and triplet state very clearly. So now let us talk about the essential criteria for a molecule to show photochemical reaction. Now, essential criteria for any kind of molecule to show photochemical reaction is the first is the molecule has the capability to absorb light. This is the first essential criteria. And second, the essential criteria is the radiation that is given to the molecule, that is the UV radiation or visible radiation, that must match the energy difference of ground state and excited state. Now here you can see a empirical MOT or molecular orbital diagram of any kind of organic molecule, and this is the energy scale. And here you can see that sigma and pi, these are the ground state energy, ground state orbital, or we can say the bonding orbital, where the sigma bonding orbital has lowered the energy, and that's why actually the sigma star having the higher in energy. So this type of energy mixing and LCAO, that linear combination of atomic orbital, is not actually I will discuss here. We'll discuss this all the thing in the MOT part of our inorganic chemistry part. So just understand here that this sigma have the lowest energy state, and that's why its antibonding orbital sigma star having the higher energy state. Similarly, pi is the much little higher energy state than sigma. This is also bonding, and also the pi star having a little lower energy than sigma. And in between there is a non-bonding orbital is also there. Now what happened that when a molecule that is present here, then a bonding orbital, so when it will actually uh, when the particular molecule actually irradiated by UV radiation, what happened, this particular electron now goes up to the anti-bonding orbital sigma star. And similarly, if any electron are present in the pi orbital, and the external light or the electromagnetic radiation energy is just matches with this particular transitional energy, then this pi to pi star transition observed. Similarly, if the electrons present in the non-bonding orbital, now depending upon the electromagnetic radiation energy, now non-bonding to pi star transition observed, or non-bonding to sigma star transition is also observed. Now you may think that why that only sigma to sigma star transition has been observed, or pi to pi star transition observed. Why not sigma to pi transition observed, or pi to sigma star transition? Why not observed? This is because that all of this particular sigma star or pi star, they contain their own symmetry, and in the transition there is a own role that calls symmetry matching. Since sigma and sigma star have the same symmetry, then according to the symmetry matching criteria, this transition is favored, not for allowed, not forbidden. Whereas the sigma and pi, between sigma and pi, there is a no symmetry matching is there, then that's why this particular transition is forbidden. Now this thing actually derived from the group theory as well as the molecular orbital theory, but since we are not dealing with right now, just you have to remember this thing, that because of the not symmetry matching, this type of transition hasn't observed. And non-bonding have their own case, like, and depending upon their symmetry, it actually somewhat matches with the pi star and sigma star, and that's why this non-bonding electron are capable to do both transition. However, sigma and pi are not shown all of these transitions, they have certain limitation. Now out of which, in our organic chemistry point of view, we are mostly focused on these two transition, that is the pi to pi star transition and non-bonding to pi star transition, because sigma to sigma star transition has required so much energy, so normal condition it will not happen. However, pi to pi star and non-bonding to pi star having very lower energy, then this type of transition has been observed in a normal photochemical situation. Now, if anyone tell about that what is the order of the transitional energy, then you can see that sigma to sigma star have the highest energy gap, and that's why the energy will be much higher. Then uh, non-bonding to sigma star have the more energy, pi to pi star have the little lesser energy, and the less energy is to non-bonding to pi star, is the lowest energy gap is there. That means this particular transition required very less energy. So this is the order of transition energy. Now in organic chemistry point of view, you have to know that type of excitation given by the class of organic compounds. Now here you can find here that sigma to sigma star transition. Which particular organic compound shows sigma to sigma star transition? Basically the alkanes which have only sigma bond. For example, CH4, methane. Methane only have the sigma bond, and that's why actually methane will show that sigma to sigma star transition. Similarly, non-bonding to pi star transition has been observed between which of the molecule contains a lone pair, like alcohol, amide, ether, thioethers. This contains oxygen. Oxygen contains lone pair, and that particular lone pairs are mainly present in the non-bonding orbital. And this actually shows the non-bonding to sigma star transition. Pi-pi star transition has been observed between alkanes, carbonyl compound, and aromatic compound. And then comes to the non-bonding to pi star. This is also shown carbonyl compound and acid derivative. And these two are well studied because these are actually irradiating, or this will be happening in presence of UV light or in the visible spectrum. Okay. So now let us talk about some kind of law of photochemistry that you must know. The first law is the Grothus-Draper law. Grothus-Draper law said that light must be absorbed by a compound in order for a photochemical reaction to take place, and the Stark-Einstein law suggests each photons of light is absorbed by a chemical system where only one molecule is activated for the subsequently reaction. Now, these two laws have no importance in your exam point of view, but for your basic understanding, you need to learn these two particular law. Now, I will look into the most important thing that for the examination purpose as well as to form your basic understanding, that is the Jablonski diagram. And this is the empirical structure of Jablonski diagram. Now you can see that there is a different diagram is there. Now I will discuss each one of them. This S0, S suggests for the singlet state, and the S0 state means the ground singlet state. S1 is the first excited singlet state, S2 is the second excited singlet state, and S3 is the third excited singlet state. Now between the two uh, singlet state, that S0 to S1, it contains different vibrational state like V1, V2, V3, V4, V5 and so on. Like, so you can say this is all electronic state, S0, S1, as well as T1 is also electronic state, and between here is also T2 is also there, and between the T1 and T2 actually there is so many vibrational state is there, and the T1 is contains the triplet state and S1 is contains the singlet state. Now, what happened that here we can say that this is one electron present here. So I just first I will rub all this thing, and this part is very important. You have to understand this particular thing very cautiously. Okay. So I just take a pen. So I draw a electron set here in the S0 state. Now, when it will be actually irradiating by UV radiation, what happened? One of the electron are actually show transition from S0 to S1. Obviously, there is the energy gap. Energy gap must be same to the irradiating light energy. Then it will show a transition, and now what happened that initially it was something like this. Now one of the electrons are actually move here. Now you can see here that initially the electrons are something like this, and after transition you can see the ground state have this electron and the excited is this electron. That means the spin of the electron doesn't change here, and when actually the transition observed between the S0 to S1 state, always remember the spin is not changing here, and that's why actually it is called singlet state. Now it also have their own quantum number as well as spin quantum number. We know that this particular have the plus half spin quantum number, and this contains the minus half spin quantum number. So if we calculate the total spin of the particular molecule after transition, then we can say that S equal to 2s plus 1. Now if we add these two, plus half and minus half, then it will be 0. So that means it will be 2 into 0 plus 1, that means 1. The overall spin multiplicity is still 1 here, But however, when it will be show a intersystem crossing, and then what happened that excited electron are contains the spin that got flipped. And so what happened that since it is now getting flipped here, so now it will look like this. So both the spin have the same direction. Now what happened that since both are the same direction, that means the both are in now plus half. Since both are in the plus half, that means now the spin s is small s is, this is small s. Now the small s is 1. That means now s equal to 2 into 1 plus 1. That means 3. Now that means we can say that now the system is in a triplet state. Now we will show the more understanding in the next slide. Here you can see this is the complete Jablonski diagram, where it will show a S0 state. Now S0 state contains electrons. Upon irradiating, one of the electron can jump either S1 state, or depending upon the energy of the electromagnetic radiation, it can jump to the S2 state also. Now if it is jumped to the S2 state, now it will bring back to the S1 state by showing some kind of internal conversion. Now this green light are actually signifies the absorption. Now a ground state electron, depending upon the energy given by the electromagnetic radiation, that is the UV radiation, now it can go via different vibrational state of different electronic state, that is the S1 or S2, and these lines are signifies different vibrational state. Now whenever it will go in the S2 state, let us imagine that it will go via S2 state, like one of the electron is there and one of the electron is there. I just simply cut down this one. So what happened that now this will bring back after losing, there is a some kind of relaxation takes place, and then it will show the internal conversion to bring back in the S1 state. Now since it is come to the S1 state, now it will uh, it can come into any kind of vibrational state of S1 state. Okay, now this will show the vibrational relaxation to come the S1 V0 state, and after that it will show a radiative process to bring back to the ground state, and the radiative process actually emits some kind of light, and that's called the fluorescence. Or the particular electron can actually show a intersystem crossing, which lead to the spin flipping of that particular system, and it will go via triplet state. Now what happened that now this particular triplet state will now go via a radiative process, which is called the phosphorescence. Now with this radiative process, the spin actually flip again, a spin flipping has been done, and now it will come to the ground state energy, that is the S0 state. So this is the overall Jablonski diagram. Now here you can ask one particular question, that why there is a no T0 state here. Where is T0 state, you may ask here. Now you can say, now we already know that T0 state means, T state means the triplet state, where the S is, the spin multiplicity is 3. Now if we need a spin multiplicity is 3, that means your both of the electron are in the same spin. Now if the ground state contains a T0 state, that means uh, we can say that both of the electrons have plus half in their spin quantum number, and if both are in the plus half in spin quantum number, then we can say that between these two particular electron, the all of the quantum numbers, that is the n, l, m, s, that is the n is the principal quantum number, n is the principal quantum number, l is the azimuthal quantum number, m is the magnetic quantum number, and spin is the spin quantum number, both are same for the two electrons. Now if the both of the two electrons have the same NLMS, this is not possible, because we know that Pauli exclusion principle says that no two electrons have the same all the four set of quantum numbers. And if T0 state is exist, then what happened that one electron is here, one electron is here, and both electron have the same quantum numbers, and this is not possible, and that's why there is a no existence of T0 state. And mostly that's why actually the compound present in the ground state in singlet form. And after irradiating by the UV radiation, depending upon the intersystem crossing or internal conversion, it will show a triplet state. So this will be very, very important for your understanding. And now we are talking about some approximate time scale for this transition. Like light absorption transition, that is S0 to Sn transition, it will take 10 to the power minus 15 second. And now the internal conversion is between a higher S state to a S1 state in any V0 term return is called, by relaxation, is called internal conversion, and it will take a 10 to the power 14 to 10 to the power minus 11 seconds. So you can see that so many less time is required to this type of transition. Then comes to the vibrational relaxation. Vibrational relaxation is within the same electronic state or the singlet state. There is a different vibration, higher vibrational energy level to lower vibrational energy level relaxation is called the vibrational relaxation. So okay, so it is vibrational relaxation. Now it will take a 10 to the power minus 12 to 10 to the power minus 10 second. Then it is come to the intersystem crossing. The intersystem crossing means the singlet state to triplet state transition, and it takes actually time, and you can find that the time is actually much higher. Then it is come to the radiative process, fluorescence and phosphorescence. Fluorescence, that means the S1 V0 state to S0 Vn state, and it will take 10 to the power minus 9 to 10 to the power minus 6 second. And phosphorescence, it will take much time because in this particular phosphorescence process the electron spin has been flipped, and that's why it takes so many long time, and that's why phosphorescence has shown uh, say so many so longer time. Like for an example, you can see the radium based watch you have already actually wear in your childhood also, and also in the roadside also you have seen some kind of glowing badge that is nothing but radium. So this actually shows phosphorescence, and it will take to come back from the triplet state, excited state, to a singlet ground state is a much longer time. That is a 10 to the minus 3 to 100 second. Even sometimes takes some days also. Also, there is certain non-radiative decays. Non-radiative decays suggests that singlet state to ground state singlet state, but in a higher vibrational state transition. Also, the triplet state ground state to singlet ground state in a higher vibrational level transition. They are the non-radiative decays, and this also takes a much longer time. So I hope this will be clear for you, and with this we have to end this particular class. So in the next class we are talking about the photosensitization, and also we are talking about the photochemistry of alkenes. So stay tuned for that particular lecture, and thank you for listening.